Hello everyone, hope you all are doing well. So, today we are going to start a new chapter of mechanical engineering named Thermodynamics. And today we'll be discussing the basic concepts of thermodynamics that will be used later in the coming videos. So, without wasting more time, let's start with the video. So, basically, first let's discuss what is thermodynamics. Basically, thermodynamics is a branch uh, of engineering where you used to learn about how the energy interacts with the environment or any two bodies. Suppose you want to know about the behavior of the heat transfer, like will how much the heat transfer will take place, or rather it will take place, or we need any external force or input to make it happen. So these types of things we study under the field of thermodynamics, and also it helps to analyze the system's properties, which are basically the cause of the heat transfer and energy interaction at the boundary. So, and it also helps us to convert disorganized or low level form of energy to higher level forms of energy. So, and yeah, what is system? System is basically that space in the universe which is concerned to your focus, which is related to your suppose your work, and anything other than system is called a surrounding, and both system and surrounding constitutes the universe. Yeah, these are the some notations that are used. So real or physical boundaries are denoted by this circle, and circular like imaginary are denoted by dotted lines, and that is mentioned here. Okay, and yeah, as I told you, universe is the cell basically constitutes of both system and surroundings. And now let's discuss about the types of system. uh, One is open system and another is closed system. Open system where like both mass and energy interaction takes place, like there are such transformation or change of mass and energy, exchange of mass and energy takes place between the system and the surrounding, like boiler, turbine, condenser, pump, etc. And closed system is a system where only the energy interaction takes place, not the mass, because it is closed. Okay, so you can see it in the piston cylinder arrangement, the thermodynamic part of that, until unless it do not exhaust any gases outside. Okay, and yeah, one more system is there, that is isolated, or you can say it is a part of closed system. Just the difference is that like when the closed system is isolated from the surrounding in terms of heat transfer, then it is called as isolated system. You can get the example of this as you might have seen the bottles that you use, thermoplast bottles that you use in winters to keep your water or tea or anything else hot. So that is not ideal, but yeah, still it is a good example of isolated system. Okay, so uh, there are basically two approaches of observation and study, that is microscopic and macroscopic. But microscopic is, you can say, as at molecular level, at micro level, and macro is at the level of that we used to study in mechanical engineering. So here we'll be concerned about the macroscopic approach. Yeah. So in thermodynamics, we are generally dealing with macroscopic, as I mentioned. Yeah. And basically this continuum approach like is the thing that helps to make the assumption of macroscopic approach, like we assume like the system or anything we are considering to be continuous rather than going at the micro level and assuming it to be discrete. We assume it to be continuous. And let's discuss about thermodynamic properties. So like uh, like properties, thermodynamic properties are like the identity of any state of a system. So these are of two types: intensive or intrinsic, and extensive or extrinsic. So like intensive properties are independent of mass, like pressure, density, specific heat, and all. Like you can see it like this way, like while you see like the properties that are not affected by mass, like if you add more mass or more content of the same composition, then the property should remain same, like density. If you will take one the density of find the density of 1 kg water or find the density of 1000 kg water, the density will remain same. So it is independent of mass. So these properties are called. Discuss about the extensive properties. Extensive properties are properties that are unlike intrinsic, are dependent on mass, like uh, volume, heat capacity. Heat capacity is MC. So yeah, this is dependent on mass definitely because mass is mentioned there. And other things like enthalpy, kinetic energy, potential energy, all are dependent on mass. And yeah, what is thermodynamic equilibrium? Like this refers to the state when two systems are in thermal, mechanical, as well as in chemical equilibrium. So thermal equilibrium means like temperature equilibrium should be there. Mechanical means pressure forces should be equal, and chemical refers to the chemical potential, or you can say the chemical, like suppose they are reacting with each other, so the reaction rate of reaction of forward and backward should be same. Yeah. So let's discuss about pure substance. Pure substance are those substances which have constant or homogeneous chemical composition throughout its volume, irrespective of its phase, like H2O, ice, steam, all are made of same component H2O. So same molecule H2O. So they are said to be homogeneous, but gas like air is not a pure substance, because you can see that the composition may vary place to place. Like that example is given here, like humidity you can see is more on coastal regions and lesser in landlocked regions like the northern India. So here you cannot say that air is a pure substance. Yeah, let's discuss about the thermodynamic state. It basically represents the condition of a system. Like it is a point basically, and path, like path is obtained by joining two like thermodynamic states, like as joined here. This is path. Mm. And yes, there are two types of processes in thermodynamics. One is reversible and another is irreversible. Reversible directly means that it should be like done with a driving force that is infinitesimally small. Suppose while the heat transfer or energy transfer, the driving force is temperature, then the temperature difference should be infinitesimally small. Then only it will be a reversible process. And also, reversible process also states that its path of forward and backward uh, should be the same. Like if it comes to the original state, like it should come with the same path. Like here it is doing. If it like from this point it goes to this point, then if it like it is reversible only if it comes to the same point, the same path. Like this pathway is not valid. Here it is mentioned forward and reverse path has to be same. Okay. And talking about irreversible processes, irreversible processes are those that are not reversible, simply not reversible, then we indeed are considered to be irreversible. And here are the some notations like just by solid line you are representing reversible, and by dotted line you are representing uh, irreversible processes. Okay. So there can be various things that are responsible for making process irreversible instead of having uh, like negligible, like having driving force that have a difference of maybe infinitesimal small, but some factors like friction, re-expansion, maximum fluid, and heat transfer through a finite temperature difference. Like these are some factors that are the reason for the irreversible processes. And cyclic processes are processes that has the same initial and final state as mentioned here. And quasi-static processes are those processes which are like which tends to be reversible because they are very slow, and they like maintain the, like suppose temperature is the driving force, then they maintain the infinitesimally small temperature difference, like not infinitesimal but very small, and process is quite slow. But we cannot say like it is a reversible process until unless the friction factor is there, like here. Let's discuss about thermodynamic properties. It is a property with the help of which we are able to calculate the values of temperature. So, like there are different properties by which we can calculate the temperature of any system. So, in case of constant volume gas thermometer, like this is basically a technique to measure temperature by using volume as the by using pressure as the thermometric property. So here you can see P equals to MRT, that is ideal gas relation. So uh, like volume is constant, so this term is constant. So P is directly proportional to T, and or we can say that T is a function of P. Okay, so like here, if we know the pressure, then we can find temperature. Therefore, pressure is the thermometric property. Similarly, in constant pressure gas thermometer, volume plays the role of thermometric property, and the same things applies to here also. And it can extend it to other things also. Other, like in electrical resistance thermometer, resistance plays the role of thermometric property, and in thermocouple, like EMF is the EMF voltage is the thermometric property. Yes. Okay. So yeah, like we have mentioned also the how, like what are the parameters that are used in ordinary thermometer, that are length and volume, like by which you are able to predict the temperature. Okay, so this is basically the ideal gas equation, and these the values of P is the pressure, V volume, and mass are gas constant, and is the absolute temperature in Kelvin. Okay, so here are some notations that are used, that may be used that are used quite frequently in the coming chapters, like P absolute equal to P ATM plus P gauge. Absolute pressure is always measured from like the bottom line, like that is zero. Zero pressure is like pressure will be zero when P absolute will be zero, and like it will be vacuum then. And like PATM is the atmospheric pressure, and P gauge is the pressure that is above the atmospheric pressure. So here the equation comes from this. Yeah. We have also studied this form of ideal gas equation. So here n is the number of mole, that is mass upon molecular weight. So this can be converted to this equation that we have studied earlier. And here R bar is universal gas constant, that is called as 8.314. Here it is written kilojoule per Kelvin, kilomole Kelvin, and R is R bar by molar weight. So, like people, students are many times confused over this R and R bar. So you can clarify now. Okay. So, uh, like, like these are some things like T is in degrees Celsius, T has also other unit of Kelvin. 0 degrees Celsius is equivalent to 273.15 Kelvin, and 273.16 Kelvin is the triple point temperature of the of water H2O, and it is 0.01 degrees Celsius. Okay, so these are some conversions. You may read that. I'll provide you link for the notes in the description. Yeah, so let's study how we measure temperature. So, like the earlier method that we used before 1954 was two reference state system. Like we use two points as the reference. One will be the melting point and one will be the boiling. So by like using two states, we are finding the temperature. Uh, Therefore, it is called as two reference states method. So you can see, suppose T is linearly varying with X and B is the constant. So we will take, if suppose like if this is for degree Celsius scale, then T of ice will be 0 degrees Celsius, T of steam will be 100 degrees Celsius, and we'll put this value in the given equation, and then we'll be able to find A, the values of A, then the values of B, and after that we'll put it in the equation, this equation, and then we will be able to find a relation for t as a function of x. So we can find it if no relation given between temperature and thermometric property, then use this. Like you can use this, but mostly these relations are given. So this is a derived uh, uh, relation between the temperature and the thermodynamic property X. You can also derive this assuming the linear behavior of temperature with the thermodynamic property. And the other method we used in the post 1954 is the symbols with reference system, reference temperature, that considered the triple point as the reference state. Like in that case, we only need one reference state because we don't have a constant. And this is like we consider this as the absolute scale because here it like the temperature of zero, like the actual temperature do not goes negative in the this temperature scale. So here you can see like how they have mentioned this. So basically saying P equals to MRT, T is directly proportional to P and K is a constant, and we can find K by one reference only. And after finding K, we will get the relation of T with the thermodynamic thermometric property. And so here we can get the relation just with one reference state. So one more thing, this you can read about it. This is an additional thing like ideal gas thermometer. Like, they are basically independent of the material construction, like to make it more standardized. So this came into picture, and this has no dependence on the material of construction. This you can read about. This you can read more. Now let's come to zeroth law of thermodynamics. Uh, Basically, in simple mathematics, you can say when A is equals to B and B equals to C, then A is also equals to C. This is the zeroth law of thermodynamics. And in thermodynamics, we say is like when a system A is in equilibrium with the system B and B is in equilibrium with the system C. So then A and C are also in equilibrium. So the concept of equilibrium is used here. And let's discuss about point and path functions. So point functions are functions like are variables whose value does not depend on the path, like entropy, volume, pressure, etc. Like you only need just the point, not the path. And path functions like heat and work are the variables that depends on the path. Like you must have seen the work in the PV diagram. If you will change the path, the work will be changed because the work is the area under the PV diagram or the V-axis. Exact differential are basically refer to the integral of variable, like the cyclic integral of variable of exact differential are zero, and its example are pressure, volume, and the like cyclic integral of inexact differential are not zero, like heat and work. So, like, uh, you can take reference from as you see the properties or state function or point functions, you will see that if in a cycle they come to the initial position, the difference is zero. So, therefore, the exact differential is zero for state function or point function, and all properties are point function as we know. So they are exact differential. And if we take heat and work, they are path functions. Therefore, they are inexact differential because, as we studied earlier, they are not dependent. Uh, like if they come to the initial position, it is not necessary that the work is zero because it depends on the path. So here you can see that we have just mentioned like if it is zero, then it is exact, and otherwise inexact. This is Gibbs phase rule. Uh, like this is helpful to find the degrees of freedom. So, like if you know the phase, you know the number of component, then you can find the degree of freedom from the given formula. And if it is minimum number of independent variable, degree of freedom is the independent number of minimum number of independent variable that are required to locate or fix and state of system. So it refers to the minimum number of parameters that you need to define the complete state of a system. Suppose you can see in other words like if you know two parameters or two independent variables. Suppose z is a function of x and y. So if you fix x and y, then z will be fixed. So this is how it is saying that degree of freedom will be fixed if the number of minimum number of independent variables are fixed. So here are some examples of this. So in a single phase, single component system, for example, ice or steam. So uh, it is single phase, so P will be one. F we have to find. C component is one and two. So degree of freedom will be two. And two phase single component system. So P is two and degree of freedom will be come out to one. And for three phase single component system, ice plus water plus steam, degree of freedom is zero. Also, you can see that like if you have ice, water, and steam at the same time, so there is only one possibility for this to happen. That is the temperature. That is a triple point state. So like you do not need any parameter to restrict this condition, because this is by happening this like if they occur at the same time, all the three things, then it is sure to be at the triple point temperature and triple point condition. But here, like ice and water can be simultaneously happen. Like you need to have at least one parameter, because you might change the pressure, then according to that the freezing temperature will be also. So here you can see the application of degree of freedom. So now let's discuss energy interaction. And so, like Perk is a boundary phenomena. So it definitely affects the surrounding. So if you will see the three cases, you can see that if we consider the battery as a system and all the other things are surrounding, so this fan will have some impact on the surrounding. So it will do some work that will be by the battery. And if you consider motor and battery both as a system, here also this fan will have some impact on the outside surroundings. So there will some work. But in this case, you can see the whole battery, motor, and fan are uh, the system. So it will not affect the surrounding, because work is a boundary phenomena and it is inside the boundary. So it will like the work here they will know work. And sign convention is work the normal system is negative while the system is positive. This is quite important to remember while doing numerical, because it lead to silly mistakes. Like what are the different types of work? Let's discuss about that. So uh, like one is for closed system and another is for open system. So for closed system, it is the area under the PV curve, and to be accurate, it is over the volume axis. And in this, the same is like the area under the PV curve is the work done, but here it is projected on the pressure axis. Here it is on the volume axis. So you can see this is for uh, closed system. This is for open system on pressure axis and this is volume axis. And yes, so here are different closed system work. For first is constant volume. So the process is isochoric, and for closed system, we know that PdV is the work done. So because there is no volume change, therefore PdV will zero and work will be zero. For constant pressure condition, the pressure is constant throughout, so the integral simplifies to P Vf minus Vi. For constant temperature, we need to do some derivation. So as we know from ideal gas equation, P equals to mRT, and P equals to constant for isothermal conditions. So P equals to C by V. When we will apply the formula for closed system of dV, and taking p as a function of c. So we will get this equation, and also resolving this, uh, we will be getting work as this. And this c can be found out from here. PV equals to c. So we must be knowing at least initial condition. By that we can find p, c, and that c we can put it here and find the work. So yeah, here you can see that. Uh, either from PV or either from MRT. Both ways you can find. And for isothermal condition, this curve, this PV curve, is basically a rectangular hyperbola, because hyperbola is just like this. PV equals to constant of P is like equal to 1 by. So this is point to be noted. During isothermal expansion, volume increases. By using the expression of closed system work for isothermal process, we will get the positive sign. Assume expansion is happening, so this work will be by the system that will be positive. And the fourth one is the adiabatic process. Like in this process, there is no heat transfer or heat interaction between the system and the surrounding. So, and it is the governing equation of this process. PV power gamma is equals to constant. Gamma is basically a adiabatic index that is the ratio of specific heat at constant pressure to specific heat at constant volume. So this is basically a gamma, and or to find the work in this process, we need to do again derivation. So we know the relation as isothermal condition. Just the gamma is here. So just same process you have to do. Integrate PdV for full system work, and on doing simple integral calculation, uh, you will get this as a final result. Later I will also be sharing these notes in the description link. You may have a look over there and you can revise it from there. And similar to adiabatic process, there is one more process named polytropic process. This is basically when you will see on a TS diagram for isothermal. For isothermal condition on the TS diagram, it will be a horizontal line, and for iso like reversible adiabatic or isoentropic process, it will be a vertical line. So between these horizontal and vertical line, all the curves are said to be polytropic process. And this, the restriction that I have just said of they will be between the horizontal and the vertical lines is governed by this, and will be always be greater than 1 but less than gamma or adiabatic index. So the derivation for work will be same as just the adiabatic, just the gamma will be replaced by n over here. So this is the representation of process. As I said, as I give you some hint just now of the like how the polytropic process occurs, or like is between the isothermal and isoentropic process. Here you can also have some analysis and comparison between them. Like you can see that uh, P Vk power gamma equals to constant is for adiabatic, and PV equals to constant for isothermal. So definitely n is in between 1 and gamma. So it will be in between these two curves. So this is the PV curve, and PV equals to constant for isothermal, polytropic, and adiabatic. So as you can see, the slope of adiabatic is highest because the value of gamma is greater than both n and 1. Therefore, it is having higher slope, and uh, you can see we have found out the slope over here. So unity is the like I was saying the steeper slope just in terms of magnitude. So don't consider the negative sign over there. So you can these are just the simple derivations of this to find the slope. Okay, so yeah, this was the result. One of the important result that slope of adiabatic is equals to gamma times the slope of hydrothermal. And this is one more observation that the value of index is increasing in clockwise direction. Like clockwise direction is this. So this is the value of n is increasing always in this direction. And let's discuss about open system work. Till now we have only discussed about the closed system work. So for constant volume isochoric, uh, yeah, there is just one difference that here the work will be VDP because in closed, like in open system, there is no like we need to define a control volume so that we can analyze that volume as a system to work over. So uh, for that we make the volume constant. Just the pressure term is variated. So uh, the work done is here is VdP, and negative sign is there because the pressure should be decreased to have positive work. If it is increased, then VdP, integral VdP will be positive, but the negative work will be negative. Therefore, the negative sign is there. And in isochoric process, it is simple to find and if you integrate, and this will be the final result. And at constant pressure, it is zero, like as in the uh, constant volume process in closed system, the work was zero. Here, the constant at constant pressure, the work is zero for open system work. For constant temperature, the procedure is quite similar to the overflow system work. Just here is VdP and a negative sign to consider, and the integration is quite simple as usual as earlier. So this will be the final result for our work, and C can be found out as I have discussed earlier. This is representing the basically the work in graphical format. And yeah, like earlier, during isothermal expansion, the volume increasing. So expression of open system, like it will be. This is just for the sign convention that it will be positive if the pressure decreases or the volume decreases. And yeah, this is quite important result for isothermal process in open and closed. They are linked in such this way. Just negative sign and VdP and PdP. Radiometric process procedure is similar, and just this change is there in every process. So you need to keep in mind rest all the processes are same, and you will come out like this result will come out. Just some changes are there like gamma and all. Yeah, this is the relation that you can remember. W work done in open system and closed system are just have a ratio of gamma, and this is for polytropic just same thing. So yeah, let's discuss about the heat. Heat is the form of energy interaction due to temperature difference. Like here the driving force is the temperature difference, and like the mathematical expression is like this, where m is mass, delta T is the driving force or the temperature difference, and C is the specific heat. So specific heat basically refers the energy required to increase the unit mass of the substance by unit temperature or unit temperature difference. So here's this. It's just a its unit. So in case of solids and liquids, there is single value of specific heat, and as case of gas, it depends on both. So here it is mentioned that like for solids and liquids, specific heat is same, but for gas, they are two specific heat, and they are need to be used at different places differently. They are Cp and Cv. So and one more thing, like for isothermal processes, the specific heat is zero. You can easily see this by the definition only, because in the definition it was mentioned that the heat required to like the heat specific heat is the ratio of the heat required to raise the 1 degree temperature of unit mass. So here the in isothermal process there is no temperature difference because the phase is changing. So the specific heat needs to be infinite to maintain this. So therefore it is infinite, and C for adiabatic is zero because heat is zero. And yeah, so here comes a question: why CP is always greater than CV? So you just you can think is it by using first law of thermodynamics. Although we have not discussed it, I will discuss it later. But for the time being, just focus on the basic concept that uh, at constant volume in a closed system world, Q is equals to U plus PdV. Here PdV will be zero because at constant volume process, U will be equals to Q. So U will be equals to Q, and U we know that it is MCV delta T, uh, right? And but in case of the process is at constant pressure, so some part of heat will be utilized uh, to do some external work, and rest will go to the internal energy, increase the internal energy, right? So this addition of work leads to the increment of like internal energy is there, but more than internal energy, the heat is there. Uh, that's why, like, because it is adding to the internal energy, therefore, the CP Q is MCP delta T. So, heat at constant pressure, all the terms are cancelled, just CP is left out. When left side CP is there, right side CV, plus some term is there, some positive term. And this results in the fact that CP is always greater than CV. So these are some sign convention. Heat supplied to the system is always positive. Heat rejected from the system is always negative. And there are two types of heat: sensible. It is the form of energy interaction by the virtue of temperature difference. Latent heat is required to do the phase change, as I told you earlier. So you can see here example like from minus 10 degrees Celsius to 0 degrees Celsius. This will be sensible heat because there is no phase change over there. This is only due to the temperature difference. But at 0 degrees Celsius, ice will convert to water. Therefore, here the heat required will be like heat required to cause the phase change is latent heat because there is no temperature difference. Then again, 0 to 100 degrees Celsius will be sensible heat, and at 100 it will boil and evaporate. So it will be latent heat. Here we should say latent heat of fusion. Here we should say latent heat of vaporization. And again, to make it from vapor to supersaturated vapor or steam, we again need sensible heat. So this was all about the basics of thermodynamics. In the coming video, we will be discussing about first law of thermodynamics, second law of thermodynamics, entropy, exergy, and many other topics. So till then, stay connected. If you have really learned through this video, then please like, share, and subscribe this channel so that you get the latest updates about this and other coming videos. Thank you. Bye bye.